Okay, hello again. We're going to do some practice specifically on an old AP chemistry exam from 2018. So we're going to go ahead and share and get started. Okay, just wanted to show you a quick, really cool, nice little website. If you go to ptable.com, that got a very cool interactive periodic table, and it shows you pretty much anything you can need to study. For instance, where are the metals in the periodic table? Where's the metalloids or metalloids? Where's the non-metals? Stuff like that. And you could expand it by clicking here to see the full picture. That's useful for electron configurations. And you can also collapse it by hitting that wide button. Okay, now let's get started here. We're going to go to, here we go. Okay, number one. Which of the following particle diagrams best represents the products when four molecules of H2O2 decompose into water and oxygen gas at room temperature? Hydrogen peroxide, just like the stuff that you use to clean yourself with, or clean cuts or whatever. Well, first of all, you kind of have to know a little bit of information. So we're saying H2O2 decomposes into water and oxygen gas. Um, let's get a little bit of some practice with writing chemical reactions. So we're going to start with H2O2. And we're going to say, okay, what is that going to decompose into? As they said, what was it? Water and oxygen gas. So water is H2O. That's a common formula you just have to know. And oxygen gas. O2. Remember, some elements are what we call diatomic, meaning they exist in pairs always. So that's things like, I think it's hydrogen, H2, O2. Sulfur is octatomic. It's usually S8 on its own, elemental. I think P is, I want to say 4 phosphorus, but there's more of the other ones. There's Cl2 gas, Br2, um, and even F2, I think, yeah. They just like to pair up. That's how they're more chemically stable. So the question is, well, how can we, notice it says when four molecules of H2O2 decompose into those two things. So we have to balance this first. So first of all, we're saying four H2O2s, but we need to balance. Here's how you balance chemical equations. Now, truthfully, you could do the whole thing where you write down each element on each side, and then you can mark them one by one and say like, here's one, here's two, or you could say there's two hydrogens, two oxygens, and on this side you could say there's two hydrogens, three oxygens, and then you can kind of go from there and do it one by one, but you really need practice doing this quick. So the way you kind of do it is you look for the thing that's unbalanced first, and then start with that. So for instance, H2 is on the left side, good. H2 on the right side, good. But we have O2 here, and we have 1, 2, 3 on this side. So the problem is you can't really change one of these things without affecting the other, right? You can't put any number that would make oxygen even, right? So for instance, if you put a 2 here, well, that would make it 4 oxygens. And then you'd have to change it. Or what I really mean is like, if you put it's because there's 3 here, that's uneven. Well, you put a 2, if you put a number like in front of these, it might change it in a way that affects the whole equation. You want to be specific, you want to be careful. So we're actually going to get oxygen, it's 3. There's no way to change it directly to 2, right? Because it's 2 over here. How do we fix that? Well, you can change odd numbers into even ones by multiplying by the lowest that lowest even value, which is usually 2. So let's say we put a 2 here. Well, then we'd have 4 plus 5. That's uneven. So maybe not 2 there, but what if we put 2 here? Well, now we'd have the 2 times that oxygen, and then the 2 here, that's 4. And we'd have 4. Then we'd have 4 oxygens, but there's only 2 oxygens on this side. So how are we going to do that? Well, what if we put a 2 here? Well, now we're going to get 4 times the hydrogen, so that's 4 hydrogens, and 2 times the 2 oxygens already, that's 4 oxygens. Then we already have the 2 times the 2 hydrogens here, that's 4 hydrogens. And then we have 2 times this oxygen plus the 2 already there, that's 4 oxygens. There you go, that's how you balance equations. Honestly, you're going to want to practice doing that a ton. That's just the general way to do it. Another consideration is after balancing it, how do you understand the coefficients between them? Well, notice, first of all, this is saying 4, right? So notice that that's double the normal amount produced. See that? So where normally if you took 2, you'd get 2 waters and an oxygen molecule, but we're saying double that by 2 because we're decomposing 4 H2O2s. So that would be 4 decomposed. And how, well, that would double everything else because you double left side of an equation. It's an equation. You got to do it the same to the right side. So I'm going to double this. And that's going to be 4 H2O molecules. And double this, and that's going to be 2 O2 molecules. So notice in total we have 4 H2Os and 2 O2s. When you draw, notice the drawings here. So we're going to look for 4 waters, and remember water looks like this, where we have a hydrogen, an oxygen, and a hydrogen. You could also show it with bubbles like that. Here's the hydrogens, here's the oxygen. So, and notice they show oxygen has a certain, sometimes they will tell you information you need to know. So point is, you're going to look for 4 water molecules and 2 oxygen molecules, and that is best supported by looks like D. See that? 2 oxygens and 4 waters. Be careful about this one. This is 4 waters, but these are 2 hydrogens. That's not the product. Okay. All right, let's look at number 2. This is saying, well, masses of carbon and hydrogen and samples of pure hydrocarbons are given above, and the hydrocarbon in which sample is the same empirical formula as propane. Empirical formula simply means the simplest ratio of those atoms. So the C3H6, how can we simplify that? Well, divide by the lowest number you can, like the greatest common factor. So that's really going to be CH2, right? Okay. So how do we determine which one is which? Well, you actually can find the mole ratio, okay, because the way that atoms are together in a because of Avogadro's number, you can actually say that the CH2, it means 2 moles of carbon and 2 moles of hydrogen. That's another way to interpret it. So we're going to take the 60 grams of carbon in one sample, and we're going to turn that into moles of carbon. Now remember, we're going to do a molar mass calculation here. So if you go to the periodic table, it's going to show carbon. And carbon, I'm sorry, this chat thing. Carbon is it says 12.011. What that means is that for every 1 mole of carbon, in 1 mole of carbon, it weighs about 12 grams. You probably should use the decimals. I'm just going to round here. Okay. Grams cancel on top and bottom. And it's just a 60 divided by 12. I think that is 5. So 5 moles carbon. Okay, but they said, well, there's also the fact that we have 12 grams of hydrogen associated with that. So if I write 12 grams of hydrogen, I can convert that. 1 mole of hydrogen, molar mass is about 1. Okay, so that's a simple 12 moles, okay? Now, the way you find the equation is you divide by the lowest number. So you would divide by 5 here, divide by 5. So that would get you 1 carbon, like the empirical formula of C3H6, but 12 divided by 5 is you cannot reliably round that to 2. So that's a no-go. Not what we're looking for. Turns out if you do that with all these, you're going to find that if you divide your 72 by 12, you're gonna get 6. And if you divide your 12 by 1, you're gonna get 12. And if you divide your 6, I'm gonna show you how to do it real quick. So your 70, what was it, 72 grams of carbon. Quickly turn that into 12 grams of carbon, 1 mole carbon. Okay, 72 divided by 12 is 6. Then if you take your regular, they said the ratio is 72 grams of carbon in the sample to 12 grams of hydrogen. We're just gonna do the molar mass again. And that's 12. And hey, check it out. Divide by the smallest. That's 1 carbon. This is 2 hydrogens. So there you go. 1 carbon to 2 hydrogens. That is the same thing as the empirical formula of propene. So that's B. Let's look at 3. In general, really high melting points are reserved for ionic compounds because their ions are attracted pretty heavily. Remember, Coulomb's law says that the charge depends on the magnitude of the force. The force of attraction, that's what bonding is in chemistry. It's a strong force of attraction between atoms and other particles. It's between those two charge magnitudes, Q1 and Q2, and and then the distance squared. So it's like as you go down, it's like kind of an exponential curve. It's sort of like gravity, the effect of gravity. So the bigger charges your ions are, the more attracted, and the closer they are, the more attracted. Okay, the more far apart, the less attraction they have, less force. Right. So they'll usually have a force on them. It's better if these are bigger charged, like +2 or +3 rather than 1. And closer is better. Okay. So ionic generally are really attracted to each other, and that's why they have high melting points. Because remember, melting point is the temperature at which they kind of separate. So it takes a lot of heat energy to separate those really charged, forcefully attracted things. So typically, ionic compounds are reserved for having very high melting points. But notice that it says in a solid phase, this has no electrical conductivity. Well, salt, like if you stuck electrodes in sodium chloride, that would be true. But what about a liquid phase? Well, the problem with the liquid phase is you actually do have some ions moving around as a liquid. Yeah, molten sodium chloride is electrically conductive. So that it says none if it's a liquid, but ionic compounds that are liquid do conduct electricity quite well. So that's an issue. But what about this one? This is still a high melting point, and even dry sodium chloride doesn't conduct it in the solid phase, but the liquid does. So this would support being ionic like that. And let's see, metallic. Well, that's still a high melting point. Metals have high melting points, but oh, this supports it too. It's got metal at solid phase is good at conducting electricity, silver and iron, and liquid phase. Yeah, it turns out if you remember, metals are those things where they have a sea of electrons. So they're atoms, and then those little electrons are kind of everywhere. So it turns out in the liquid phase, that happens too. The positive ions are surrounded by those negative electrons and they move around. And so, yes, so in a solid phase and a liquid phase, they both conduct electricity. So it looks like D is the best one. Network covalent is just about a bunch of covalent bonds together. And it would make sense for substance X to be network covalent because it's a covalent compound. So it's not going to be conductive in solid phase or liquid. It has to be dissolved in the liquid usually. Okay, so D fits that data. What about 4? Based on the information in the table above, which of these has the highest boiling point? Remember your types of intermolecular forces. The whole idea is intermolecular forces are forces between molecules. They're not actually holding atoms together. They're holding actual molecules together. So these are bonding forces. Ionic, notice that's some of the highest energy to break apart. Covalent's pretty good sometimes, but ionic is usually the strongest. Metallic is pretty up there with covalent. Okay. So in general, how do we determine the intermolecular force? So first of all, the name is derived just from exactly what it is. If it's an ion dipole force, that literally means an ion is attracted to a compound that has a dipole. How original. So for instance, a sodium ion attracted to water, that's why water dissolves things so well, because that overcomes that force, and it's very thermodynamically um, uh, thermodynamically favorable to those interactions. You get more energy than it takes to do it. An H bond is usually between it's a polar bond between a hydrogen and something that's bonded to oxygen, nitrogen, or fluorine. So for instance, water can hydrogen bond with itself. It's pretty strong. And that's because the hydrogen of the oxygen, the hydrogen that's bonded to this oxygen is bonding to another oxygen. That is a hydrogen bond right here. The oxygen bonding to hydrogen allows for that hydrogen bond to occur. Dipole-dipole literally means two polar compounds, two compounds with dipoles coming together. ICL, for instance, bonding to ICL. And dispersion forces is everything has dispersion. That's the weakest force. Everything has it. That's usually why compounds that only have those are gases at room temperature, like methane. Those are nonpolar compounds. Okay, so that is how you determine that. Sorry. Okay. So when I look at this, basically notice that it says that which will have the highest boiling point. Well, the stronger your intermolecular forces, the stronger the force that holds together these molecules, the more energy it's going to take in the form of heat to break them up. So the things that form the stronger bonds, like hydrogen bonds, dipole, those are the best. Pentane, sorry, just has a bunch of carbon and hydrogen. It has dispersion and it has quite a bit of surface area, but it doesn't have anything like hydrogen bonding. So let's look at the next. Oh, butanol, that can hydrogen bond because it has an oxygen, so it can accept the hydrogen bond from something else, but it can't bond with its own molecules of butanol because it just has an oxygen bonded to carbon. It needs to have an oxygen bonded to fluorine, nitrogen, or oxygen. How about propanoic acid? We'll check this out. Oh, look, it's a hydrogen bonded to an oxygen. So therefore it can give hydrogen bonds, not just accept. Accepting is just oxygen or nitrogen, but this one can give because it's got an oxygen bonded to a hydrogen. So therefore this one should be the most attracted to itself. And so propanoic acid, because it can form intermolecular hydrogen bonds because of that, the OH group. Okay, let's go to 5. Remember, gases, we usually model gases as they're like perfect and they have no bound the bonds in them. Excuse me. There's really no bonding at all between we treat them like bouncy balls. They just bounce around, and we say they're like perfectly elastic collisions, and they're not attracted to each other at all. But that's just not true. So turns out the van der Waals equation predicts this, and it says, well, there's a correction. Some gases have a lower pressure than the ideal gas law predicts. How does that explain that? Well, it turns out the gases are in real life attracted to each other very slightly, dispersion force. And because they're attracted to each other a little bit, they're not fully going to have time to smash into the container walls. So therefore, there's not as much pressure because that's what pressure is. It's a force from those gas molecules hitting it, force per square inch. So C. How about 6? Equal volume of solutions in 2 different vessels are represented above. If the solution represented in vessel 1, KCl, aqueous, dissolved in water, then what is vessel 2? What is it going to be? Well, let's see. So let's count so this is talking about molarity here. Remember, molarity is moles per liter. So it's the same volume. So the moles is only going to make the difference in molarity here. Well, we can count the actual individual positive ions. because we can find the molarity just based on those. Because if it's a 1-to-1 ratio between KCl, it could be a different ratio with something else in vessel 2. Let's take a look. So for instance, we have these are potassium ions, the black one, so 1, 2, 3, 4, and it's a 1-to-1 ratio KCl. So it looks like this would be basically a 4 moles per liter solution because we have the 4 ions. Okay, how about vessel 2? Well, now we have a lot more, but notice the question is, can these be KCl in vessel 2? Well, notice that it's not a 1-to-1 ratio. It's not just K and a Cl. There's if you count them, there's some positive ion, but there's 2 negative ions for each positive. So it can't be KCl. So that represents CaCl2 better. But the question is it the same molarity as vessel 1 or different? And if you count the ions, notice it's double. So we got positive 1, 2, 3, 4, 5, 6, 7, 8 as opposed to 4. Therefore, the molarity is actually going to be twice as large. You can just count one positive ion for that. You don't have to find all the other ones to do the math. So there you go. That's 6 is D. 7. Sometimes they give you reaction and they actually are giving you like details about the volume and stuff. That might not be necessary. It's just saying which best represents the species that react and chemical species produced in this reaction. Well, notice what we're taking. This is actually acetic acid. It's a weak acid. Keep that in mind, and a strong base. Now some of you are probably going to point to this and say, oh, I remember this. The overall net ionic equation is H plus comes together with OH minus to form water. That's an acid neutralization. But here's the problem. Weak acids don't give up H plus fully. They're stuck a little bit, right? So there's still going to be some weak acid going on. Okay. So it wouldn't be correct to say H plus and acetic acid because you're still going to have some of that exist. Most of it will exist as the full form. So one of these two is the best. Notice that this includes sodium, which is not really reacting. Notice it's a spectator ion. It just floats around. It's just for charge balance. Just make sure that containers aren't charged and crash into each other in the lab. It's just how physics works. So therefore, C would be the best because the weak acid is intact a little bit and it's reacting with the OH minus, and the sodium ion is not present because it doesn't react. It's just there. Okay, 8, standard reduction potentials. There's an equation for this. Whenever you see when you have the half reactions of a cell and they give you the voltage, the E naught, that's the standard. That's what that means. You can calculate it for the cell. So it turns out E of the cell standard potential is actually going to be the E reduction minus E oxidation part of the cell. By the way, you're probably like, well, wait, I've seen an equation that says E cathode minus E anode. Which one is correct? They're both the same. There's actually a saying, red cat and a red and an ox. So red cat and I saw a red cat and I saw an ox next to each other. That's how you couple them together to remember that. The point is you take the reduction potential and subtract the oxidation potential. The more negative something is, the more negative its E is, the more likely it is to be oxidized. Okay. So therefore means lose electrons, the potential to lose electrons. So therefore, the more negative one here is actually going to be the zinc. Okay, so we're going to say the one that is more negative will be oxidized. So the reduction one should be negative 0.74 because it's a larger value, minus the smaller one, negative 0. What was that? 76. Okay. And that's like saying negative 0.74 plus 0.76, which should give us negative 0.02. And that would actually be, wait a second, hold on. Sorry, hold on a second. Okay, so I got it now. I just switched some terms around, actually, to be honest, but we're good now. So actually, what I meant was, it is true that the more negative the potential is, it will be oxidized, but that means it is the reducing agent and will be the reduction end of it. That's actually what I meant, sorry. So it's actually the opposite here. So we're saying the reduction part is the more negative one. So that's actually going to be negative 0.76 minus the other one, 0.74. So it's like negative 0.76 plus 0.74. Wait a second. I messed up. I just realized I just did the math wrong. This is positive. I was right. Wow. Okay. I'm not very good with electrochemistry. I'm sorry. Point is, negative. The more negative potential is, the more likely it will be reduced. Sorry, the more likely it will be oxidized. So I was correct to put these where they were. I just did the math wrong. And it's plus 0.0 plus 0.02. It's D. I am very bad at math sometimes. Let's go right to 9. 9 is saying, well, the ionization energies of the unknown element X are listed on the table, which of the following is most likely the empirical formula formed by this element X in phosphorus. Remember that if this is ionization, it's about forming ions. So remember phosphorus on the periodic table. You gotta be able to look at the periodic table and say, based on this group, this will be a certain charge. For instance, group 1 is +1, group 2 is +2 ions. Group 15 or 5A is +3. Sorry, -3, then -2 for this one, -1. Okay. With some variance in the transition metals. So P is actually usually 3 minus. It's in that column. Okay. So P3 minus. Then the question is, what is the charge on X? Notice ionization energy means how much energy it takes to turn something into an ion. Notice that it takes some energy to make X into X plus, and then it takes more energy to make it X2 plus. And then notice the biggest bump in energy is from the second to the third. You immediately go from 1450 to like 77000. It's a big jump, huge jump. That means that the second ionization energy, which is when it turns into X2 plus, that is actually going to be the proper ionization energy before too much energy is required. So it means it will naturally be 2 plus, because anything else will require too much energy. So it tends to be an X2 plus ion. You can cross these just like a normal compound and say this is X3P2, and that should be the answer, which is going to be C. All right, how about number 10? Which of the following correctly compares periodic properties of two elements, provides an accurate explanation for that difference? Well, looking at these, how about this? The first ionization energy of aluminum is greater than that of boron. Ionization energy increases as you go up to the right of the periodic table. And so they're saying that aluminum is greater than boron. So here's boron, here's aluminum. Aluminum is below boron. It's not greater ionization energy, so that's already wrong. How about the first ionization energy of F is greater than that of 0? Well, that is true. Fluorine is more up and to the right of oxygen, or not more up, more to the right. And what about the this thing is tearing me apart. Okay, what about okay, so it is true the first ionization energy of F is greater than that of oxygen, but it says oxygen has a higher electronegativity. Ionization energy increases up and to the right, so does electronegativity though. Fluorine is more up and to the right than oxygen. It has a greater electronegativity, so that's wrong. The atomic radius of calcium is larger than that of magnesium because the valence electrons of magnesium experience more shielding. Well, C is actually that's the right trend, the atomic radius trend. As you go down and to the left, it gets bigger, the radius. But it isn't true that magnesium has more shielding. So what that means in shielding is like you have your nucleus, and then around it, the electrons are pulled into the nucleus. And the outermost electrons don't feel as much of an effect than the inner electrons because they're closer. Coulomb's law. The closer you are, the more effect you feel. And so therefore, it turns out calcium is a bigger atom. See, here's calcium. It's bigger than magnesium. And therefore, it's going to have a different shielding. It's going to have magnesium is going to have less shielding than calcium. Calcium is going to have more shielding because it's bigger in radius because it's down more, and it's so down below magnesium. The bigger you get, the lower you get, the bigger. And so the outer electrons aren't going to feel the tug as much as magnesium's. So these are all wrong except D. All right. Let's talk about 11. On the basis of the information above, what is the approximate percent ionization of HNO2 in a 1 molar HNO2 solution? Well, if we say HNO2, I'm just writing the reaction down for you so I can analyze this. And they give us a K, which is 4.0 times 10 to the negative 4. And they're saying, what's the approximate percent ionization given a 1 molar HNO2 solution? Well, we can actually use an ice table. Why? Because you need an ice table to tell you the percentage, because that's actually what these KAs are. They're telling you the ratio of products to reactants. So we need that. So ice table. So whenever they say like percent ionization or percent product formed, we usually need that. Well, these are all aqueous, so we all count them. Initially in the solution, it says we start with a 1 molar solution. We don't know, well, how can we start with products initially? It's just dissolved HNO2, 0 products originally. Then we're going to have some change in X. We don't know what it is. And then we're going to get 1.0 minus X. The same change, but reflected as a product, so plus X plus X. Notice there's these, if they had coefficients, those would reflect in a plus X, but that's not the case here. So, all right. Now we're going to set up our Ka expression. So we're saying the Ka is equal to the H plus products over reactants. So, okay, and let's input the numbers here. So X times X, or X squared over HNO2. Now notice it's 1.0 minus X. Notice it said in the problem an approximation. approximate. What that means is we're saying that, well, this is such a weak acid approximately that we're barely going to get any removal of the original molarity at all. So that removal of the minus X is negligible. So we're saying forget that. That's our assumption. So guess what? Ka, or 4.0 times 10 to the negative 4 equals x squared over 1. Huh. That's easy. Square root it, solve for x. And I think x would be 0.02. All right. Now, they say percent ionization. Well, the whole idea is compare it's like a fraction. So remember the whole part of it was the original 1.0 molar. And we just determined that the molarity of the products are 0.02. So we're looking at the fraction of how much is actually created or ionized versus the original. That's just what a percent is, part over whole in general. So that's times 100. I think we would get 2. So just about 2%. And that is D. Okay. That should agree with the answer. Number 12. The equation above represents an elementary step. When they say elementary step in a mechanism, like how a chemical mechanism works, of reaction steps, elementary means it is the simplest way you can look at it, and it's just the actual molecules coming together in the 1-to-1 ratio or whatever ratio. And so usually when you write a rate law, here's the context. So let's say we have H2O2 yielding water and oxygen, then we could balance that, remember. Usually the way you'd write the rate law is rate equals K times H2O2, and then you would, so we want to say to ourselves, well, you would think it would be squared because that's the coefficient. That's not the case. You have to analyze kinetic data to do that with like the table and the experiments. So the only way you can say this is 2 goes there if it is an elementary step. Okay, elementary means it's the most simple mechanistic explanation. And therefore, if it's an elementary step, you can write a rate law from an elementary step. So therefore, you can write a rate law from this equation because it is an elementary step. If it was an overall equation, you couldn't. You'd have to use data from something else. So you're going to say rate equals K, that's the rate constant, times, well, remember, we're talking about the rate, and the rate starts, of course, with the reactant reacting or decomposing, whatever. And you can say squared because this is a elementary step. So C. 13, a balloon is filled with 0.25 moles of helium at 273 Kelvin and 1 atmosphere is allowed to rise to the atmosphere. Which the following explains what happens to the volume of the balloon as it rises from ground level to an altitude where the air temperature is less and the air pressure is less. Compare the temperatures and compare the volume pressures, for instance. Well, notice the temperature is quite a bit less, goes from 73 to 20, but the atmosphere is a lot less of a fraction. It's like thousandth, right? Well, either 100, I think it's 1,000th if I'm looking at it correctly. Point is, you go from 1 to 0.1. That's a big change compared to the temperature. So guess what? We should expect that this balloon will increase in volume because there's less molecules holding it together. And so those intermolecular bonds are being overcome. All right. And so 13, let's see. So the volume will increase because a decrease in the air pressure will have a greater effect than the decrease in temperature. Yes. And again, that's because, well, the air pressure is most important because we have our balloon. Remember, on Earth, we have air pressure already pushing it down. And as you go up into the stratosphere, whatever, you have a lot less of that pushing back. And so therefore the gas can expand because there's less force on it from the air. So that's how you do that. A. All right, let's look at this one. Equimolar, when it says equimolar, that means the same molarity. Don't worry about that. Of these two chemicals are placed in a separate, previously evacuated, means all the air is out of it, so no reactions can take place in the air. Rigid or not moving 2-liter vessels. Each vessel is attached to a pressure gauge so we can see the pressure. Temperature is both the same, 300 Kelvin. Liquid is to remain present at the bottom of the container at all times, so it's not just a gas sample. And let's look at the change in pressure over time. So here's the time, here's the pressure of that's methanol. I'm not sure you have to derive that name. Notice that it immediately shoots up as this warms. Clearly, the intermolecular forces between the methanol molecules are starting to break up, and it's allowing it to turn into a gas inside, increasing the pressure. So 14 is saying, how is methanol, what's happening to it as it is placed into this evacuated vessel? Well, just like I said, there's first of all, is it a chemical change? It's not a chemical change. Remember, we talked about physical changes. Those are the same before and after. So this is the same chemical, just a different state. So it's physical. Covalent bonds are a chemical change. Breaking bonds and rearranging them, that's a chemical change. Clearly, the intermolecular attractions are just holding them together, and they're overcome. So D. All right, 15. Value of Kp for the evaporation. Kp is the same as, remember, your products over reactants is the same thing. But guess what? When you look at this, it's going to be CH3OH liquid turning into CH3OH gas. And guess what? You don't count liquids in your equilibrium expressions, only gases and aqueous solutions. Therefore, only the gas actually deals with the directly, because look, it's saying, well, the Kp is saying, what's the ratio of the product's pressure to the ratio of the reactants? But guess what? There is no reactants because that's a liquid, so we cancel that. It's just the products. So the product directly determines the Kp. And so if you do the math, if you do a little ICE table if you want, you can see that. So ICE, first of all, cancel that. We don't even care about that. It's a liquid. Initially, it's 0 in the cylinder. There's a change in the vessel, and it was, what was it, 0 point, it changed. We'll just look at the pressure, the equilibrium pressure, 0.196. Well, guess what? Plug that in to your Kp. That's the only value. So the Kp is the equilibrium pressure. And so therefore it is 0.196 or 0.2 if you're round. Okay, let's look at 16. Temperature of the methanol is increased. Oh, it's increased from 300 to 400. And that increases the pressure to 0.30. The experiment is repeated with the same chemical, but half the mass. Well, just think about it logically. If there's half the mass, you're going to get half the gas because there's a relationship between moles and pressure. Okay, so guess what? If you half it, it's a direct relationship. You're going to half your pressure. So it starts with 0.30 atmospheres. You're going to take half the mass of that, and you're going to raise it from 300 to 400 again. Well, guess what? You're going to get half the 0.30 atmospheres. You're going to get 0.15. That's pretty simple. 16 is A. Compared to the equilibrium vapor pressure of methanol at 300 K, which was this, that's what that represents. Equilibrium vapor pressure of the other chemical at 300 is what? Well, some considerations here. Remember, vapor pressure is the higher, the more volatile your chemical is, the more atoms that come off of it. Sorry, the more atoms that are gaseous, which creates more pressure, because more gas molecules equals more pressure, right? So remember, not only is there, both of them have hydrogen bonding, but we have 2 carbons in this one. So it's a bigger molar mass and more surface area for this to bond. So therefore, we would expect less gas molecules to come apart. So it's going to be lower. And yeah, because it's London dispersion forces, right? because there's more carbons in the other molecule and they hold on greater. All right, 18. Which of the following Lewis electron dot diagrams represents a molecule that is the most polar? In terms of polarity, it's like saying, look at the difference on the periodic table. I don't think you're going to get electronegativity values to compare. So just use your best judgment. As you go up and to the right is more electronegative. First of all, you should also understand that boron, if you look at the vesicle structure, notice it has an empty orbital on boron. So that electrons pair on top will not push those fluorines down. So even though the way they drew it, a better representation would really be all equal. So the force is the same in all directions. There's no net direction. So that actually is nonpolar, even though fluorine and boron are really quite polar bonds, just the way that's oriented the molecule. Best choice here would probably be probably B. 18 is B because so this one is a nonpolar one. There's a pole between sulfur and chlorine. That's about the same. And if sulfur, doesn't matter if sulfur was fluorine, if it could be, because you're gonna have a pole one way and the other way. It's a tug of war that nobody wins. So there's no net direction. Then between A and B, well, bromine is actually less electronegative than chlorine. So there's a bigger difference in electronegativity between bromine and fluorine than there would be chlorine and fluorine. So it's going to be B. That's the most polar, the biggest electronegativity difference. Remember, electronegativity is like how well they hold on to their electrons. Fluorine is a hog, it pulls them towards itself in the bond. All right, Coulomb's law again, we remember the bigger the ion and the smaller the distance, the better charge. This one's saying which anions will have the strongest interactions with nearby water molecules. It turns out some ions can actually react with water because they're small and charged enough. And think about it, using Coulomb's law, the smaller they are, the closer they're going to be to each other and the more attraction, right? Like physically small. And the more charged they are, the better the attraction. So the more charged, the better immediately. So it's either S2 minus or tellurium 2 minus, sulfur 2 minus, or wait, telluride ion, I think, and then sulfide ion. Anyway. And then, well, the smaller ionic radius is the best because the smaller apart you are, the better attraction. So actually it would be C for 19. All right, 20. Which of the following equilibrium systems represented below will the amount of products at equilibrium increase if the volume of the reaction vessel is increased at a constant temperature? This one is about, I think this is Le Chatelier's principle. The whole point is that when you make a change in a system, how will the reaction respond? Will it make more products? Will it shift to the right side? Will it make more reactants and shift to the left side? That's why there's a double arrow to represent these. And so the question is, well, we're saying that the volume of the vessel is increased. Well, notice that for this one, this caught my eye because, well, we have 1 mole of gas on the left side and 2 moles on the right side. The 2 moles occupy a bigger volume. So if I stretch out that volume of that container, well, guess what? It's like saying, well, how can we, the change is that now we have less volume. How can we, we have more volume. How can we make it so that our gas has less volume? Because you want to do the opposite thing that it originally was, right? So again, we are increasing the volume of the container, and the change to counteract that would be to decrease the volume of the container by adding more gas to the system. So it should be A actually, and the reason why it's A is because, so if we increase the volume of the container, the change we want is to make more gas to decrease the volume. All right, and so we're actually going to pick A because, well, notice that if we make products, we're going to have more gas on the right side than the left side. And as we stretch the volume of the container, we want to make more gas to accommodate for that change. So it's actually going to be A. Okay. Alrighty, I think that's going to be good for this part. Thank you.